Welcome back to Integral Calculus. In this video, I want to introduce you to Euler's formula. And yes, that name is pronounced Euler, despite how it may look. This is named after the Swiss mathematician Leonhard Euler, who was active in the 1700s and is perhaps one of the most prolific mathematicians to have ever existed. Euler got his hands in just about every facet of mathematics that you have or will come across. And perhaps most telling, there is a Wikipedia page that tracks topics in mathematics that were discovered by Leonhard Euler, but are named after the next mathematician to come along and do things with them because Euler already had something too similar named after him. So in other courses, you may come up with things that have nothing whatsoever to do with Euler's formula that are still bearing his name. First, and perhaps most important, the exponential function, e to the x, the natural base e, 2.7182818, etc., etc. Yes, exponential starts with the letter e, but that e actually is for Euler. And some people call this Euler's constant. We've seen previously that we can expand the exponential function as the power series. N goes from 0 to infinity of x to the n over n factorial. It will also be useful to us here to have a couple of other power series in mind. Specifically, sine of x is the sum, k goes from 0 to infinity of negative 1 to the k, x to the 2k plus 1 divided by 2k plus 1 factorial. And cosine of x is the sum, k goes from 0 to infinity of negative 1 to the k, x to the 2k all over 2k factorial. Right, so those two power series expansions will be useful to us. They will come up a little bit later on, but we're going to focus for right now on the power series for the exponential function. And we're going to ask a very simple question. What if the x in the exponential function was not a real number, but a complex number instead? So we're going to work with the imaginary number I. Remember, is defined so that I squared is equal to negative 1. And you've probably played around with powers of I at some point in the past. Anything to the 0 power is equal to 1. Anything to the first power is just that thing. The definition of I gives us that I squared is negative 1. I cubed would then be negative 1 times I, which would be negative I. And then I to the 4th power. Well, if you take negative I times I, that would be the negative of I squared. I squared is negative 1, and the negative of negative 1 is positive 1. And so that brings us right back to where we started. And we just go through this cycle. I raised to powers cycles through positive 1, I, negative 1, negative I, positive 1, I, negative 1, negative I, and on and on and on forever. So if we try, instead of evaluating e to the x, we evaluate e to the ix, well, we should be able to just use the same summation that we used for real numbers. We'll have ix to the n power divided by n factorial. This might make a little bit more sense if I expand it out a little bit. So I guess we will have ix to the 0 over 0 factorial plus ix to the first over 1 factorial plus ix squared over 2 factorial, ix cubed over 3 factorial. And that really gives us the entirety of the character, because remember, I to the 4th power is going to behave the same way as I to the 0 power, so we'll see this cycle repeating over and over again. But of course, anything to the 0 power is just 1. I'm going to explicitly write that as 1 times x to the 0, even though that's not really going to do much of anything here. And likewise, I'm going to call this I times x to the first over 1 factorial, even though we know that simplifies to just I times x. But I think seeing the pattern is going to be useful. And then we'll have I squared, which is minus 1. And I'm actually going to write this as plus minus 1 times x squared over 2 factorial, and plus minus I times x cubed over 3 factorial. And we'll continue on with these exponents. 1 times x to the 4th over 4 factorial, I times x to the 5th over 5 factorial, negative 1 times x to the 6th over 6 factorial, negative I times x to the 7th over 7 factorial, 1 times x to the 8th over 8 factorial, so on, so on, so on. And whenever we're dealing with complex numbers, kind of the default first thing to do is reorganize things so that you have the real part and the imaginary part separate. So let's try doing that in a different color pen. We'll take all of these terms that have an I in them, and we'll split them off as a separate grouping. So we have 1x to the 0 over 0 factorial plus minus 1x squared over 2 factorial plus dot dot dot. And then we have I x to the first over 1 factorial minus I x cubed over 3 factorial and dot dot dot. And then for all of the things in the imaginary part, I'm going to factor out the common factor of I. And we end up with a fairly nice pattern. In the first grouping, we have all of the even values of n in an alternating series. In the second grouping, we have all of the odd values of n again. In an alternating series. Right? The first term is positive, the second term is negative. The third term, had we written it, would be positive, the fourth term would be negative, and so on and so on and so on. We know how to express even and odd numbers. We can write n is even as n equals 2k for some value of k, and we can write n is odd as n equals 2k plus 1, again, for some value of k. And now I want to start thinking about what k is going to be. If we plug in k equals 0, then we get n equals 0 and positive. That's our first term here. If we plug in k equals 1, then n equals 2k, so n is equal to 2. and we want that to be negative. And we'll continue on this pattern. When k equals 2, we will have n equals 4, which should be positive. When k equals 3, we'll have n equals 6, which should be negative, and so on and so on. And then for the imaginary part, when k equals 0, we get that n is equal to 1, which comes out as positive here. When k equals 1, 2 times 1 plus 1 is 3. And we should have a negative value for that. Well, that's not too difficult to handle. Right? Notice that in either case, whenever k is an even number, we want the positive term, and whenever k is an odd number, we want the negative term. So if we just add up all the k's going from 0 to infinity, we're going to have x to the 2k, and it will be n factorial, which in this case is 2k factorial. And then if I put negative 1 to the k power, that will give me a positive 1 for an even value of k, and a negative 1 for an odd value of k. Same thing over here. If we add up all of the k's from 0 to infinity, if I put negative 1 to the k, that will give me positive for even k and negative for odd k. And then it was x to the n, but n is now 2k plus 1. And it was n factorial, but that's now (2k plus 1 factorial). And those should be very familiar to you. I wrote those down near the beginning of the video. This first thing is the power series expansion for cosine of x. And the second summation is the power series expansion for sine of x. Let's bring back the original left-hand side. E to the ix equals cosine of x plus I times the sine of x. This is Euler's formula. This is the complex definition of the exponential function. The most famous place to evaluate this is at, x equals pi. Gives you a very interesting result. So we have e to the I pi is cosine of pi plus I times the sine of pi. Cosine of pi is 1. Sine of pi is 0. And then this equation is typically rearranged ever so slightly to write that e to the I pi plus 1 is equal to 0. This equation is sometimes called Euler's identity. This is one of the most beautiful equations that was ever written down. It combines the fundamental constants of all of the math that we have dealt with up to this point. 0 is the additive identity. 1 is the multiplicative identity. Pi is the circle constant or the trigonometry constant. I is the imaginary base. E is the natural number. These 5 fundamental constants kind of define all of the math that you have used up to this point in your academic career. In the year 2000, there was a poll among mathematicians and physicists to name the most beautiful equation ever written. This came in second. Other entries on the list, I wasn't able to find it when I was recording this video, so I'm not sure what order they were in. But we had things like Newton's second law, F equals ma. We had Einstein's equation, E equals mc squared. And the most beautiful equation ever written according to this poll the definition of the number 2. 1 plus 1 equals 2. So that is the level to which this equation is elevated in the pop culture of mathematics. Does it deserve that? I don't know. But the general form that's still above me definitely does. This form is the sometimes called the polar form of a complex number, and most of the work of complex analysis is built around using this formula. We're not going to get that far into it, but I think it's worth knowing and understanding and being able to use. So, just really quickly to make sure that you do understand it, because this video has gone on pretty long, rather than trying to get into something a little bit uglier, let's just have you take a look at evaluating e to the 3i pi over 4. See what you get with that, and I'll see you in the next video.